Hi guys. So far we covered very interesting concept, that is motion of charged particle in a magnetic field. So we try to calculate the magnitude of the force and direction of the force for positive charge and negative charge, and how the path affects in the presence of magnetic field for both positive charge and negative charge for any angle. So we came across, so if the velocity is perpendicular to the magnetic field, it makes a circular path, and the component of velocity and magnetic field makes an angle of 90 degrees, and if it enters at any angle, so then it makes an helical path, because the perpendicular component and parallel component they resolves, and the perpendicular component is responsible for to make a circular motion, and parallel component to make that distance between two circummotions. So this is so far I discussed about of a charged particle in a magnetic field. What about if you take a conductor which carries a current? If that conductor, if we place in a magnetic field, not a single charge, now this time we wish a current carrying conductor placed in a magnetic field. So as like a single charge, will it experience any force? And if it experiences any force, we shall try to figure it out what its magnitude and directions. So today I would like to discuss how a current carrying conductor behaves in a magnetic field. Let's see first an experimental demonstrations which is given by Walter Louis. So he's explained the same experimental demonstration. So the experimental setup consists, what he is carrying is a magnet, a strong magnet, natural magnet, and that natural magnet is kept in a current carrying a conducting wire. Right now it is not applied any current or no. So this is a conducting wire. This is a conducting wire and which is kept in a magnetic field. So this is a natural magnet. So magnet having two poles, suppose if we can take direction, so this is the direction of magnetic field, I don't know which is the north pole and which is south pole, and if a current passes through this conducting wire, maybe along in this direction, now this current in the conducting wire is perpendicular to the magnetic field direction. So let us observe, is these two will interact or will it two cause any type of force? Now moreover that, here we need to mind about directions, since current is also having directions along the magnetic field. So when we switch on current, when he switch on the circuit, and due to depends upon the direction of magnetic field, here you notice the wire pulled down and the strength of the force such a like that it is capable to drop its supports. Now the force which is act on that conducting wire is in the downward direction. So that's the reason the supports which held the wire is fallen. Now what happens if it's right moment when he changes the direction of current? The direction of current change by the changing the switch direction. Now this time the force, the wire is jump up. So the direction of the force on the wire is in this direction. So finally I can conclude at here in the two cases. In the two cases, when we apply current to a conducting wire. So that conducting wire is kept in the presence of magnetic field due to interaction of the current carrying conductor, because the conductor carries charge, and we already learned charge experience a force in a magnetic field. Now because of that, the total force, so here keep in mind the force experiencing due to external magnetic field, not the magnetic field of the charge carrier by itself. Yeah, when charge is moving in a conducting wire, it creates its own magnetic field. So that magnetic field is not the cause adhere to act force on the conducting wire. So here the force is due to the external magnetic field. Now the external magnetic field cause the force on current carrying conducting wire. So let us try to get expression for this. Now here the magnitude of the force is too strong. It depends upon the strength of the magnetic field and depends upon the amount of current which is passing through the conducting wire. Now let us try to derive how this get force expression on conducting wire which is kept in the magnetic field. Now let us finish this how the force will be act at here when changes the current direction. Now this time the force is at upward direction. So let us try to derive an expression for the force on a current carrying conductor in a magnetic field. So I have taken a current carrying conductor, so this kept in a magnetic field. So let me take this magnetic field which is piercing the screen, which is going inside the screen. So I don't want to put the cross marks on the conductor because I need to add some extra components. Suppose this is a conductor, this conductor of length L. So this is a conductor of length L. So the conductor of length L and area of cross section, it's having area of cross section is capital A. Now this conductor is placed in a uniform magnetic field. Now as the experimental evidence we saw that in the demonstration, so due to the interaction of the current, suppose a current is passing through this wire. Suppose if I connect this to as an external circuit to a cell, that the electrons are moving inside that. Now if the electrons are moving, we need to remember electrons are having average drift velocity. And before that, so what is the force expression for a charge carrier? If a charge is moving in a magnetic field, the force expression of a charge is the Q times V bar cross B bar. That is the force expression on a charge. For a moment I am dropping the directions. Let me find out the magnitude first. Now I will drop this video also for a moment, later I can introduce that. Now in this current carrying conductor, how many charges are present? That's what first I need to figure it out. Let capital N is the number of charges. So I can say that capital N equal to number of charges which equal to small n times area times length. Here small n equal to the number of free electrons per unit volume. The capital N I can take the total number of electrons in the conductor. So I can write that capital N equal to total number of electrons in the conductor. Total number of electrons in the conductor, capital N equal to small n times area and length, because it multiplies gives to us volume. So here's little n, that little n equal to number of electrons, free electrons per unit volume. Number of free electrons per unit volume. So I came to know it here, the total number of electrons equal to n times A times L, and each electron having a charge of Q. So if it is having each of charge, that charge either you can write as in terms of E or Q. So I can rewrite the expression, the force F equal to N times A times L times here the Q equal to charge of V cross B. The above expression has changed at here. So here we already know all the terms, but here the Q, I did not take charge of electron as Z for a moment. So here Q is the value of charge, the value of the charge or magnitude, not the direction. To electron you can just substitute negative E, there is no big deal. And here V is the velocity of the charge, but we know that electrons move in a conductor with a drift velocity. So the V, I added a suffix D, that is known as drift velocity, Vd. Now I need some pre-knowledge. That pre-knowledge is that how we would define current. If you remember from early chapters, current I equal to N E A V D. Here E is the charge of electron, and from this we already write that I upon A, which is known as current density, which is J. This is little j. Current density J equal to current per unit volume, which equal to N E V D. Suppose here E equal to Q. In this moment E equal to Q, the current density J equal to N Q V D. Why I am going for that? Because to me in the above expression I am having like that character set here. So in this above expression, if I can write like that, so I would like to change the above expression F equal to AL times J cross B. So here J is a little j. How can I write that J? J is nothing but current density. Here J equal to N Q V D times A. J equal to NQVD times A, because current density, so it's a scalar, so we can keep that. So if you can see that clearly, in the place of N and Q and VD, NQVD, so I can take that as J, which is at here, since J equal to NQVD. And rest of the terms AL is already there in the expressions, so I just kept out and I have taken that one J cross B. Or for your understanding, if I just modify the above expression like that, so then it's easy to get you. So I wish I would like to write this by rearranging the terms like that. I wish I can write that NQVD is out times A and above all cross B. So which is I'm missing it here? I'm missing the component L. Yeah. Now in the place of NQVD, we can substitute J. Now that becomes J cross B. I hope this is something is meaningful. Now if I want to calculate further, F equal to AL upon J is nothing but current upon A, current density, current per unit area, times cross B. It's multiplication, cross product. So A gets cancelled and F equal to L times I cross B. Now the magnitude of the force expressions F equal to L I cross B, you can write that Bi sin theta, the cross product of two vectors. Now here a formula A cross B equal to AB sin theta. So we can get that magnitude of force F equal to IBL sin theta, or F equal to, it's easy to remember to me, I used to pronounce this one BIL, Bill sin theta. But whenever you apply the force direction, please mind carefully. So where is the cross product? The cross product is between the magnetic field and current carrying element. So these expressions we can write for a straight current carrying conductor, because for current carrying conductor, if it is straight, we can get easily measured its length. Now force is directly proportional to strength of the magnetic field, and it's directly proportional to the amount of current which is passing through the conducting wire, and is also directly proportional to the length of the wire. And above all, it also depends upon the theta, the angle between the current carrying the component of the velocities, not the component of velocity, just the velocity, the direction of current and the direction of magnetic field. So here the theta is between B and I. So how can you write the same expressions if we have some crooked like this conducting material or current carrying material like this? So if you have like that kind of material, conducting material, so we need to find the each part elemental length dl. By using integration, we can find the total length. We can find the total length by using integration technique, rather than if it gives a straight wire, then things gets easy. But if it's given as an irregular conducting wire, so by the times the formula everything gets same, but we need to do here the extra work. That extra work, if we can get the total force, I can write in simple manner summation sigma times the dl. So here dl equal to the elemental length of the conducting wire times I cross B. So here we need to do some extra work to find the elemental length rather than it is straight. If it's straight, we can make it use directly in the formula. The things is easier. But when it is irregular shape, then we will go for integration to find its total length. So this is the expression for force on a current carrying conducting wire which is kept in a magnetic field. So this force F equal to, you remember, it equal to BIL sin theta. So or F equal to L times I cross B. So later we can use certain rules to find its direction. The same left hand rule and right hand rule we can use to figure it out what is the resultant force direction on the current carrying conducting wire.